Hello and welcome to Lapping Analytics. My name is Jimmy Lapping. I'm a psychologist and statistician with an interest in a range of topics, including research methods for the social and health sciences. And in this video, I'm going to talk about a non-parametric approach to trends and change in single case designs. It is an approach that I introduced in a video last week for the type of design that you see here in the middle, which is an interrupted time series design, which means in this case, okay, the same case or subject was measured over time 10 times. But it's an interrupted time series design because there was a series of measurements which we call the baseline phase. Then there is an intervention or a treatment of some kind, and then you have another series of measurements, and you expect a change in the outcome of interest starting the onset of the treatment, right? So this is what I introduced last week. But I already mentioned that, okay, this kind of approach, either in its entirety or part of it, can also be used for different types of single case designs. Because, well, there are different types of single case designs. One is where you have an intervention at some point, but there are also single case designs where there is no intervention. This, for example, here is an example of a single case observational design in which a student, let's say a medical student or a nursing student, during a trimester of the study program had weekly simulation trainings, and each simulation training was rated on a number of things, including on an overall scale going from 1 to 4. With 1 being poor performance, 2 being borderline performance, 3 being satisfactory performance, and 4 being excellent performance. Now, for the people who don't know what borderline is, so poor means unsatisfactory. 3 means satisfactory. Borderline is basically a kind of performance that it's neither unsatisfactory nor satisfactory. It's kind of, there are some minor lapses in performance which are actually not okay, but in a real patient setting that would not have any serious consequences for a patient's health. So it's kind of it's the kind of student that would pass by the skin of their teeth. You know, it might be just enough to pass that exam. Now, some people might say, sure, okay, these are 1 to 4 ratings, that's integer numbers. We have 10 measurement occasions. We just draw a straight line, and here we have a linear model for our change over time. But of course, there is a number of assumptions underlying this approach. First of all, that the measurement occasions or assessment occasions are equally distant, so there are equidistant time points, so meaning the number of days between each two measurement points is constant, and also the difference between each two subsequent ratings is the same. So the difference between poor and borderline, for example, is the same as between satisfactory and excellent, which, well, there is no guarantee. Right? It's possible that the distance between excellent and satisfactory is larger, for instance, than the difference between poor and borderline, or between borderline and satisfactory, where the difference might be relatively small. So you could say, okay, the difference between 1 and 3, that's 2 ranks, just like the difference between 2 and 4 is also 2 ranks. But to say that there's equidistance between subsequent rating categories, well, that is maybe a bit of a stretch. And apart from that, well, this straight line here, where does it get? It gets somewhere to 3.7. What is that? Is that satisfactory? Is it excellent? You know, so there are quite a few questions, of course, raised by this linear approach. Now, so one alternative is to find a non-parametric approach, which respects the ordinal nature of the ratings. Now the problem is that many of those methods require, the ones that account for a trend, they tend to require a larger sample size, a larger number of measurements, a much longer time series, which in practice isn't realistic. I mean, a student may have 10 simulation training weeks in a trimester or in a quarter of a year, but not 50, for instance. So you cannot say, we just increase the number of measurements just so we can do more fancy statistics. That doesn't work. And well, some other non-parametric methods, they don't account for trend at all. It's just some people might say, okay, we split the first and the second half and we do some non-parametric test on that. Well, the approach that I introduced in a video last week can, in part, part of it can also be used for this kind of single case observational design. So we don't need to make linearity assumptions as a starter. What we are interested in is simply the difference between the first measurement and the last measurement, because, well, in this assessment context, we would hope that student performance is better in the last simulation training than in the first, if the course focuses on the same skills that are being trained on a weekly basis and assessed on a weekly basis, well, one would want to see an improvement in ratings throughout that program, right? That in this case 10-week program. By the way, the fact that I make this a straight line doesn't mean it's a linear approach. I might as well have just drawn a vertical line here from 4 until 2, which is the absolute difference in ranks that we are interested in. So there is a difference of 2 ranks from the first to the last measurement occasion. And the question that we ask in the non-parametric approach that I propose is whether this difference of 2 ranks is notable in the context of the whole distribution. Now, what do I mean by that? Well, given 10 measurement occasions, there are 10 times 10 minus 1 divided by 2 equals 45 pairs of assessment occasions where you can calculate a change. So for instance, from measurement 1 to measurement 2, that's one of the 45 pairs we can compare, and here there would be an increase of 1 rank. Whereas, for instance, from occasion 1 to occasion 3, they result in the same assessment, so that would be a 0 difference. That's what we have here, while from 1 to 2 that would be in this bar here. So that is what we do for all 45 pairs. So for instance, in this case, the one that we are most interested in is the difference between the first and the 10th occasion. That's 2 ranks. And that is what we find here. Just like if we compare the 9th occasion with any of the others, we would also find for number 1, number 3, number 4, number 7 compared with 9 would also be a difference of 2 ranks. So this is a surface here. So this is the distribution of all those differences. So we have 45 pairs. Some of them result in a -1 difference. For instance, here from the second to the third occasion we see a regression. So basically a move down of 1 rank. So that's one of these observations that contributes to this bar here. Then there are also 0 differences, 1 differences, and 2 differences. So this is the distribution of all those 45 differences. Here you don't see frequencies, but I use probabilities because it gives a bit of a grip on, okay, where do the differences go? And the key question now is whether the difference that we find is substantial or notable in light of this distribution. Basically the question is here, okay, we now observe a difference of 2 ranks between first and last assessment occasion. What is the chance that we find at least that difference, either upward or downward, So at least 2 points, 2 ranks of difference, or further away from 0. So that means anything of 2 or further to the right, or anything minus 2 or further to the left, well, that surface is 0, because there are no minus 2 or minus 3 differences, for instance. So what is that? What is that bar? So in this case, we are only talking about this bar here, this surface, which is almost 20% chance. And now this is the data. So we have an almost 20%, of those 45 differences result in a difference of 2. And we scale that back to the original sample size of 10. If you want, I mean, I'm going a little bit fast in this video. If you want the full procedure, the full explanation of this, I refer to the video that I introduced last week, the link of which you can see in the first in the first picture that I showed of this video. So at the start of this video. So I scale that back to a sample size of 10, so that would mean nearly 2 successes and just over 8 failures. Then in the absence of any prior knowledge, I use a beta 1-1 prior distribution. And that's those two, so the data scaled back to a sample size of 10. So 45 comparisons scaled back to a sample size of 10. Plus a beta 1-1 prior distribution gives a posterior distribution with a median of nearly 0.22 and a 90% credible interval running from almost 0.07 to almost 0.45. Now, in the video that I shared last week, I proposed that if this 90% credible interval is entirely below 0.5, we can speak of a notable trend. In this case, it's a positive trend because the point estimate is positive. So yeah, this interval is entirely below 0.5. That's why we say yes, this change of 2 ranks is a notable change in light of the whole distribution. So basically we are, so in the approach that I explain in that video that I shared last week, I basically say in the context of an interrupted time series design, there are 6 steps to follow. But basically now we only use the first 3 for designs where interventions are absent. We only use the first 3. Which are they? The first step is to carefully inspect the time series to see, okay, what is the kind of change? Is the change from beginning to end a strong change relative to the rest, or do we see a lot of dispersion halfway as well, changes of 2 or 3 ranks all the way, because then in that case this difference of 2 might not be that notable. So study the time series. Second, inspect the distribution of all differences. And third, calculate these statistics for the trend and draw your conclusion. So in this case, the non-parametric approach for trend indicates yes, there is a meaningful trend, there is a meaningful improvement from the beginning of the program of the student. Here the student had a borderline rating all the way to excellent in the last one. I hope that's useful. So this is just this shows how we can apply that non-parametric approach for trends and change in single case designs when an intervention is absent, when you simply have an observational series of measurements. And in the next video, I will also explain how you can use these steps and the other steps of the approach that I introduced last week for interrupted time series designs when you have actually a randomized block design. That will be the next video. Anyway, I hope you find this useful. If you have any questions or suggestions, feel free to drop them in the comment section below this video. And for now, thank you for watching, thank you for listening, and I hope to see you in a next video. Bye bye.